Hello everyone, hope you're doing well, and welcome to another lecture in nonlinear programming. And in this lecture, we'll talk about another iterative method, which is the conjugate gradient method. So the idea here is to have a more computationally efficient iterative scheme for solving quadratic minimization problems originally, and then we extend such method from nonlinear problems to nonlinear problems. So let's consider the linear, call it CGM. Let's consider the linear conjugate method. So let's consider let's consider first the quadratic minimization problem. That's minimizing p of x, which we define as a quadratic function given by this one, x minus p transpose x, so x in Rn, and A is an n by n symmetric and positive definite, and B is a vector in Rn. And in the previous lectures, we know that the gradient of P at x is just ax minus b, and the Hessian of P is just the matrix I. And from the assumptions of A, we know that P of x is strictly convex. So this means that the quadratic problem is so therefore means that this minimization problem, call it hashtag 1, or wait, let's just change it. I'll just make it a hashtag 1. So from the previous lecture, hashtag 1 is equivalent to solving the linear system ax equals b. Call that hashtag 2. And now let's define the residual function r of x, or simply the residual, as the vector ax minus b. Okay. So that's the residual of the linear system. So the idea to describe the idea of conjugate directions of conjugate gradient method, the CGM here is actually originally aimed to solve linear systems of the form hashtag 2. So here, let's start with a family of general a general scheme for the conjugate gradients, where we don't assume yet that we have the gradient, and that brings us to conjugate direction methods. So here's how it works. To start with an initial guess. That's not. And we let the following set of vectors, P O P1 up to P sub n minus 1 as a set of linearly independent vectors in Rn. And because of this one, we can write any vector x in Rn in the following form. So that's x equals p vector x0 plus this linear combination of the set here. So that's alpha I pi. And that's for some scalars alpha I here. So by applying the definition of p of x here, then we can write p of x as the following. So we have 1/2 of, I'll just distribute the transpose here, transpose plus summation of alpha I pi transpose and minus 1, and then a times this one minus 1, and then we have minus b transpose x0 minus the summation of alpha I times, let's say, pi transpose p. Note that p transpose pi is just PIB transpose, or PI transpose B, I, or B, just B. Sorry. Okay. And minus 1. And then by some expansion here, you can simply simplify this one as the following. Because if you multiply these two summations, you will get the following. So that's 1/2 times summation of, it's actually a double sum, but I'll just write it as a single summation. So this runs from I and j equals 0 to n minus 1. So that's alpha I, alpha j. And then p sub I transpose. And then you have a here. A times p j. I just use two indices here. And then plus the following, that's summation of alpha I times pi transpose times ax naught minus b for I0 to n minus 1 plus p of x o. And that's actually from this one and this one, and then the products involving these terms here. Okay. So, so we have this very term with lots of terms, or rather a quadratic function with lots of terms. So let's simplify this one by imposing the following condition. if we choose those set of vectors such that this scalar here, it's pi transpose A, P sub j is 0, when the indices are not equal, then what will happen is this double summation here will be simplified as the following. And the whole thing will be simplified as this summation of alpha I squared, because what we'll retain here is the instance when I and j are equal. So that's when I is equal to j. So that's why you have alpha I squared, and then pi transpose A pi. And we can just close it there. And plus alpha I pi transpose ax naught minus b. That's for I equals 0 to n minus 1, and plus p of x naught. Okay. Of course, you will get 1/2 here because each value here when I is equal to j occurs twice, so you will have twice times this one, and then you will cancel here 1/2. Okay. So what happened now is this quadrat with these assumptions on the vectors, this one is composed of n one-dimensional problems. In fact, they are quadratic. That's because of this one here. And with this condition here, brings us to the following definition. It says that we have a set of non-zero vectors PO P1 to Tn minus 1 in Rn, and that's said to be, or rather, not yet. Let me mention another thing. We have this set of vectors. Oops. Okay, I was disconnected, so let's go back. So again, we have the following definition. We have a set of non-zero vectors given by this one. And we call this A conjugate. And that's with respect to the symmetric and positive definite matrix A. And that's if the following scalar pi transpose A pj is equal to 0. That's for all I not equal to j. So what's the good thing about this A conjugate vectors is that we have the following lemma. It says that any non-zero A conjugate vectors P1, Pn minus 1 are linearly independent. And here's a short proof of this one. So let's assume we can write 0 as this linear combination of this vectors here. So that's COVO plus up to CL. I'll just use vectors L, P sub L. So that's equals to the sum of oops, that should be nope. This is not actually n minus n. I just any number of vectors. Let's say Pn. Also here, make it PL, and then this linear combination here is equal to Cj Pj. That's j equals 0 to L. And suppose this holds for some real number CO up to CL. Then let's multiply each equation by Pi transpose A. So we have 0 equals CO P sub I transpose A, CO plus C1 Pi transpose A P1 up to CL times Pi transpose A PL. And then equivalently, by factoring out this one, this is equal to Pi transpose A times this linear combination here from Cj Pj. That's from j equals 0 to L. Okay. And then we can also put this one inside, and then we have the following, that Cj times Pi transpose A Pj. That's j equals 0 to L. And then because from the definition of a conjugate, the ones that will be left in the summation is at when j is equal to I. So that's Ci Pi transpose API, because this is equals to 0 if j is not equal to I. Okay. So you're left with just one term here. Now, what we know about this one is this is greater than 0 because A is symmetric, or rather A is positive definite. Since this is a scalar, and you have a positive scalar here which is equal to 0, then this only implies that Ci must be equal to 0 for all I. And that proves the linear independence. So going back to that set of non-zero A conjugate vectors, we can now write this minimization problem here, because this one has become a problem in terms of I, or rather alpha i's. So by #2, we can now write